the multiple regression model. So far, we have studied a simple regression model where the outcome dependent variables y is a linear function of only one explanatory variables, independent variable x, and we used examples where y is the food consumption expenditure and x is the weekly household income. In reality, it's more likely that y depends on more than just one explanatory variables. For example, let's say we want to estimate demand function, demand for coffee, and the quantity of demand depends not just on the price of the coffee, but also maybe on the price of tea, substitute or price of milk, complement goods, and might depends on income, so more than just one variables. To explore such a situation, let us look at the multiple regression model. What does it mean by multiple? Because now the model we are going to estimate has more than one explanatory variables. And I hope you will see that actually most of the results of our simple regression model will continue to hold with only minor changes. For example, like when we interpret the marginal impact of x, now we need to be aware that we have quite a few x, x1, x2, x3. So when we interpret beta 1, beta 2, then we need to hold everything else constant. We also need to change the degree of freedom, as you will see in a moment. And we need to have an additional assumption on the characteristic of x as well. All right, let's look at an example first. Big Andy's Burger Bun. The management of Big Andy, so now I need to make decisions on two things. First, whether to increase or decrease the price. Second, whether to advertise or not. So in order to make an informed decision, certainly they will need to understand the effect of price and advertising spending on the revenue. Okay. Theory suggests that sales here is the monthly sales revenue in a particular city, depends on price, average price of the goods sold by the burger bun, and advertising expenditure in this way. And we will be interested to know what's the beta, particularly the sign of beta 2. What's the beta 2? So beta 2 is the partial derivative of sales with respect to price. So now I'm using this curly the partial sales, partial price. This is a partial derivative, means that hold advertising spending constant. Okay. So if beta 2 is positive, then that would say the demand is inelastic. So we know that price goes up, low demand will say that quantity that burger bun can sell decrease, and sales revenue will be equal to price times quantity. So price goes up, quantity decrease. If the demand is inelastic, then decrease and quantity is smaller. Say price increased by 1%, quantity decreased by less than 1%. So in the end, the sales revenue goes up. So if this beta 2 is positive, then demand is inelastic. In contrast, if an increased price, if the demand is elastic at one increase in price will result in more than 1% decrease in quantity, then sales revenue will decrease. So if it is negative. Also, the management will be interested to know whether beta 3 is bigger than or smaller than 1. If it is bigger than 1, that means that spending $1 extra on advertising results in more than $1 of increase in sales revenue, which is good, right? Which justifies advertise. If it is less than a $1 increase in advertising expenditure, only results in less than $1 increase in revenue. So in these cases, advertising might not be a good idea. All right, from the economic model, we set up this econometric model. We add the error terms to capture all the other factors that might affect sales revenue. And Big Andy has a random sample, 75 franchises in similar sized cities. So that means in the sample N is 75. So there are data of sales, price, advertising spending from city I is equal to 1, 2, 3, 4 until N 75. Here, in order for us to properly estimate beta 1 and beta 2 and beta 3, we need this EI, the error terms, not correlated with the right-hand side variable, not correlated with price or advertising. So, or more strongly, we say that conditional on price and advertising, the error terms has a mean 0, not correlated. We cannot use price advertising to predict E, the error terms. So, taking conditional expectation on both sides, we get this. Conditional on price and conditional on X, which here is price, advertising expenditure. We have this equation. So now, because it's 0, so it dropped here. And this is the multiple regression function. If we draw it, visualize it, draw a graph, is something like a plane like this. So the vertical axis is sales. The two horizontal axes, advertising and expenditure, is actually. And the dot point here is the data point. And we fit rather than the regression, than the line into the scatter plot, data points. Now we are fitting a plane to the data points. Okay, more generally, we have a model, a linear model like this. Yi is equal to beta 1 plus beta 2 xi2 plus until beta k times xik plus error terms. Okay, let xi to be 1. Here 1, you can think that is xi1, which is equal to 1 is a constant terms. Okay, xi2, xik, so there are k element in here. And the x collect all the data of x, right-hand side variables, from observation 1 to observation n. And if these x are strict exogenous, which means conditional x, we cannot predict the error terms of I. Then we have this, taking expectation on both sides of this equation, conditional x. So because x is data include xi1, xik, when we condition on it, we are treating it as a known constant. Okay, so this beta 1 is constant, beta 2 constant, this constant, we can take it out. Then we get this is equal to this plus this terms plus E, which by our assumption is equal to 0. All right, we do need a few assumptions to estimate beta. It's quite similar to the simple regression models. First, MR1, data generation process is indeed this way. You should think that beta 1, beta 2, and beta 1, beta 2, beta 3, beta 4 until beta k, they are true values of the parameters. They are constants. Okay, that's data, the sample are generated by this process. That's our econometric models. First assumption, second assumption, strict exogeneity. That means this conditional expectation of EI, conditional X, not just conditional 1 XI, okay. Conditional on both X1, X2, X3 until Xn. Remember, this is our big X is equal to 0. And this implies the expectation of EI is 0. To see this, we can apply this law of iterated expectation. We first conditional on Xi, conditional on X, and then take this can be a function of X, then take expectation on all X. So the inner expectation is conditional on X, the outer expectation is taken expectation with respect to X. And we know that our assumption is 0. So now E0 is just equal to 0. Similarly, the covariance of EI and XJK for J is the J's observation, K is the K component of the X. Remember, we have X1, X2 until Xk, right? Xi1, Xi2, Xik will be equal to 0 as well. This is equal to 0. Okay. So you can think that E is EI X I is equal to 0, and this is vector, okay, k by 1 vectors, okay. And again, this can be derived by the law of iterated expectation. Condition X. So condition X, we know Xi, so Xi is constant, we can pull it out. And this is 0. So E Xi times 0 is 0. Okay, that's MR2. MR3, conditional homoscedasticity. So it says that the variance of EI conditional on X is sigma squared. Okay, and this is the same. That means it does not depend on I. No, that is sigma squared does not depend on I. So it's also the same as variance of EJ conditional X. And that implies the variance of YI is X squared as well, conditional X. MR3, MR4, conditionally uncorrelated errors. So we need EI-EJ to be uncorrelated, conditional X. So remember, expected value of EI, conditional X, is 0. So covariance of EI-EJ, conditional X, is just expected value of EI-EJ, conditional X. We need it to be uncorrelated. So in the cross-sectional data, this means that there's no spatial correlation among the error terms. If our data are time series data, then that means there's no series autocorrelations. And this might not be true. We will look at situations where this is not true later on. Okay, MR5. This is slightly different from the simple regression model. No multicollinearities. It says that there's no exact linear relationship exists between the explanatory variables. So now we have more than one explanatory variables, right? So let's suppose to see this. Let's suppose xi2, the second explanatory variable, is is twice the third exponential variables. Okay, now in our model is yi is equal to beta 1 plus beta 2 xi2 plus beta 3 xi3 plus beta k xik plus ei. Okay, so now if this is exactly twice of this, then we can actually plug in this. So we'll have beta 1 plus beta 2 times 2 plus beta 3 xi3 plus beta k xik plus ei. So now if we run estimations, we can estimate beta 2 times 2 plus beta 3, but there's no way for us to separate. And let's call this beta tilde 3. We can estimate beta tilde 3, but there's no way for us to separate what's beta 2 and beta 3. Actually, there are many combinations beta 2 and beta 3 that give you the same value of beta 3 tilde. So in these cases, beta 2 and beta 3 are actually not identified. Okay, so we need to avoid such kind of situations. So that's our MR5. MR6, error normalities. Basically, it says that conditional on X, our error term is normally distributed, and that implies that conditional X, Y, the outcome variables, is also normally distributed. And this allows us to do finite, to conduct inference and testings in finite samples. All right, so we have a general model. Yi is equal to beta 1 plus beta 2 xi2 plus beta k xik plus error terms. We want to estimate beta 1, beta 2, beta k. So the least squares principle is to choose beta. Now I'm using beta to collect beta 1, beta 2, beta k. So this is k by 1 vectors. To minimize the sum of square errors, so sum of square errors, plug this one in here, you get these objective functions. This is well-defined quadratic problems. Okay, this is a quadratic function, so it's well-defined, which means that it has a minimum and it has globally unique minimums. Okay, and the solution is called ordinary least square estimator solution to these problems. And if we compute the solution, let's call beta hat. Compute a beta hat at a particular sample with a particular sample, we obtain the least square estimates. So now you want to distinguish estimator and estimate. Okay. So the least square estimation allows us to estimate beta, but we have additional parameters, right? Remember, we have one more parameter, which is sigma squares. How do we estimate this? Under assumption in R1, in R2, and R3, we know that sigma square is the variance of error terms, which is expectation of EI square, right? So this expectations, to estimate this, given this, in light of this formula, we can, to estimate sigma square, we can first predict the residuals. So EI, this is called EI hat, which is the data yi minus the predicted value of I, which is B1. Remember, B1 is estimate of beta 1, B2 is estimate of beta 2, so on and so forth. So minus B1 plus B2 xi2 plus until bk xik. So we can predict this residual. Then square them, because we have square here. Square them, add them up, divided by n minus k. Okay, here in simple regression models, when we estimate the error variance, we sum this, square this, divided n minus 2. where layer K we only have two variables B1, B2, right? So when we are computing these quantities, we kind of fix B1 and B2. So we lose 2 degrees of freedom. That's why we minus 2 from n. So the degree of freedom here is n minus 2. Now, because we have k variables, including a constant, okay, these k variables, so we are fixing this b1, b2, b3, and bk. So we actually lose k degree of freedom. So we need to divide. So instead of rather than dividing n minus 2, we divide this by n minus k. So that's the difference between multiple regression model and a simple regression models. All right. So when we run the regressions, estimate the simple regression models, we can also using R squares, okay, to measure the proportion of variations in the dependent variables that is explained by all the explanatory variables. Same formula, okay. Sum of squares due to regression divided by total sums of squares. With finite samples, we have this Gauss-Markov theorems. It says that if assumptions MR1 to MR5 hold, the least square estimators are the best linear unbiased estimator, blue. Okay, best means what? Best means it has a minimum variance among, remember our beta hat, or B1, B2, or B1, B2, BK, they are now random variables. So the variance is smallest among the class of linear unbiased estimator. And it's linear because it's linear function, or B, or maybe I'll call it beta hat, just don't be confused. B, in our textbook is B, but I might call it beta hat. We put a hat on top of beta to denote that it's an estimate. So this beta hat of B is a linear function of Y. That's what it means by linear. It is unbiased. That means the expected value of this beta is equal to true value. Okay. If we additionally have MR6, the error terms are conditionally normally distributed, then this square estimator, the B's or beta hats, is also normally distributed. And this, from here, given this, we are able to do interval estimation, hypothesis testings with finite samples. All right, when the sample goes to infinity, we have this large sample properties. So here we are typically interested to know two properties, consistency and asymptotic normality. What do we mean by consistency? It means that as sample size goes to infinity, approach infinity, sample size become bigger and bigger, the probability that the estimator will be close to true value becomes 1. Or in other words, the probability that we are going to get things wrong becomes 0. Okay, and we can actually show that the OLS estimators are consistent by using law of large numbers. Asymptotic normality, it says that the estimator approaches a normal distribution, a bell-shaped distribution as sample size n increases. And again, we can show that the OLS estimators are asymptotically normally distributed by a central limit theorem. Okay, let's go back to our examples. Andy spoke about. So now we have Andy spoke. The management has a random sample, 75 random sample data from 75 cities, and we can estimate these models using OLS regressions. So the command is LM, and data, you load data into the R stored in the object in my samples, and do the regression, output result to an object, save the results to an object called model 1, then summarize it, save the summary result into an object called s.model1 and display it. That's the regression result. So here, this column here tells us the point estimate of these coefficients. Intercept is estimate for beta 1, or is actually B1. Price here is the coefficient of estimate of beta 2, we call it B2. Adverse is estimate of beta 3, which is B3. We can also calculate the standard errors, which is estimate of standard deviation. Remember, B1, B2, B3, they are random variables, so they have a expected value, which because these estimators are unbiased, so they are equal to, say, for B2 is negative 7.9079, and they have variance or standard deviation. We estimate them. We call them standard error. That's this column. This column is t-value, which is equal to the point estimate divided by the standard error. For example, 18.722 is equal to 118.9136 divided by 6.3516. Okay, t-value. So we can use this to do hypothesis testing. Whether the intercept, whether beta 1 is different from 0 statistically, or is statistically significant. And you can follow the hypothesis testing is pretty much the same as what we did for simple regression models. But here there's a kind of quicker ways we can check these p-values, or actually the regression output already tells us triple star here. It says that, okay, triple stars means significant at 0.1%. If we choose alpha as 5%, and we can compare this p-value, p-value is less than 2 times 10 raised to the power E16. 2e minus 16 is a scientific way of writing the numbers. It's equal to 2 times 10 raised to the power negative 16. So it's very, very small. It's certainly less than 5%. Then we can conclude that the intercept beta 1 is statistically significant at 5% level. Similar for other coefficients. We can also rate the R squares here is 0.4486. And residual standard error is 4.886 with 72 degrees of freedom. So remember, our n is 75. And we have we lose 3 degrees of freedom, B1, B2, B3. So 75 minus 3 is 72. And when we estimate this, so when we estimate the sigma square is sum of the residual square divided by n minus k, right? So this 4.886 is the standard error is square root of this. You get 4.886. We can also do the interval estimation. We're going to utilize this. Remember, model 1 is where we run the LM command and store the results into an object called model 1. So now we can compute the 95% confidence interval. Okay, so that's the 95% confidence intervals. We can also let R compute the variance covariance matrix of B's. Remember, we have B1, B2, B3, and they are correlated with each other. we use this VCOV of this. So that's the variance covariance matrix. So the diagonal element, which is the variance. So if we square root them 40.34329990, we get a standard errors. And the off-diagonal element is the covariance between, for example, this one is the covariance between B2, that's the coefficients of the price, and the B1. And you should observe that this matrix is actually symmetric. Okay, must be symmetric. Covariance between B2 and B1 is the same as covariance between B1 and B2. Okay, they are the same. Okay, we can do hypothesis testing. Looking at the significance of a single coefficient, we can directly read from the output here. Okay, and this is the same as what we do for the simple regression models. Okay, let's now test for whether the demand is elastic or not. So here are the procedures we want to follow. Set up the null hypothesis. The null is we want to test whether beta 2 is bigger than or equal to is non-negative or negative. Okay, so null hypothesis is beta 2 is bigger than or equal to 0. Alternative is less than 0. So this is a one-tail test. Okay, so that's first step. Second step, we need to create a test statistics. So now here important sense that we act as if the null hypothesis is the equality beta 2 is equal to 0. Why we can do so? Here's the reason. This is valid because if we reject nulls for beta 2 equal to 0, if we reject null, then we also reject for null if beta 2 is positive. Okay, so let's assume that this is true, and we can create t statistics. Right, t is equal to b2 minus 0 divided by standard error of b2, which is t distribution with a minus k degree of freedom, and choose that's step 2. Step 3, choose the level of significance alpha. Let's choose 5%. Compute the critical values. So we have t distribution, very similar to normal distribution, but now note that it is one-tail test. So we are finding that critical value, so that our alternative is beta 2 is less than 0. So we are looking at this tail. We want this tail to be 5%, the probability of to be 5%. So which is we can use this command alpha qt compute the percentiles corresponding to alpha, and with degree of freedom this many, which is negative 1.666294. So that's the critical value here. Then the rejection region is this region. And if the value of test statistics is less than negative 1.66, we reject the null hypothesis. So step 3, step 4, compute the value of test statistics. This is quite easy. Just negative 7.908 divided by 1.096. We get this value, and clearly it's less than the critical value. So we reject the null. So indeed the demand is elastic. In a similar way, and this will be your home exercise, you can also test for whether beta 3 is bigger than 1 or less than 1. Similar way. Alright, so now we are ready to answer the question, should Andy's burger bun increase the price or not? So we estimate B2 to be negative, which is, we also conduct hypothesis test, reject the null that beta 2 is non-negative. So indeed, the demand is elastic In such cases, it's actually a good idea to decrease the price. Decrease. If the management decrease the price by 1%, demand will increase by more than 1%. Sales normally will increase. Okay, so this we can answer this question now. And should Andy's burger bun advertise or not? And beta 3, if we conduct test, we're going to find that it is indeed bigger than 1. So now it's such a good idea, because now if we spend $1 more on advertising, we can actually bring in like $1.86, so which is a good idea. So actually the Andy's burger bun should advertise. Okay, if yes, how much dollar to spend on advertising? Actually, we cannot, given our current model, we cannot answer this question. But we can include, say capture the, well, here our current linear regression is saying that, okay, the more advertising, the higher revenue is going to be. But in reality, you should think there's a limit. We should approaching a certain limit, right? So the margin effect might be non-linear, right? So we didn't capture this. So if we capture this, we should be able to answer how much dollar to advertise.